So our next topic within normal distributions is z-scores. I told you there was a lot we knew about normal distributions. Our objective, given a normal distribution, convert a data item to a z-score. All right, what do we know? Well, we know what a normal distribution is, a graphical display of normal data in which the data tend to cluster around a central value, the mean, with fewer and fewer values occurring as you move away from the mean. So we kind of did like this. We went from the top of the bell curve, and that's the mean. We know it's symmetrical, and we know that as we move standard deviations above and below, the further we get from the mean in either direction, the fewer and fewer data items that appear in that area, okay? We also know what a standard deviation is, a measure of how spread out the data are. So what is a z-score? Well, a z-score, given a normal distribution, again, this does not work if the distribution is not normal. The z-score is the number of standard deviations a value is from the mean. Okay, so the z-score tells you, I am 1 standard deviation above the mean. I am 1.7 standard deviations below the mean. The z-score tells you where you stand relative to the mean. It measures a data item's position relative to the mean in a normal distribution. Here's the formula. The z-score is equal to the data item minus the mean divided by the standard deviation. What the z-score allows us to do is to standardize normally distributed data sets. That allows us to compare scores, to compare data items that are from different normal distributions. Okay, let's take a look. Give me a moment here. Get myself set up properly. Okay, I got a couple of examples for you. Let's talk about newborns and their weights. Of course, newborns, the weights of newborns is normal. Generally, a baby comes out, a newborn, and the weight will be, it'll be some weight, but they're all kind of clustered around a mean. There are very few newborns that come out that weigh way above the mean or way below the mean. They all come out pretty close to the mean. In fact, the mean weight of newborns is 7 pounds. I think I was 6 pounds, 15 ounces, so I am barely below that 7-pound mean. My brothers, I think, were both heavier, as a matter of fact, so they would be above the mean. And the standard deviation is a very small 0.8 pounds. So we're all really clustered around 7 pounds. Okay, we're all very clustered. The weight of newborns is normal, of course. What is the z-score for a weight of 6 pounds? In other words, how many standard deviations away from the mean is a 6-pound newborn, given that the mean is 7 pounds. Okay, so z-score equals the data item minus the mean divided by the standard deviation. Okay, what's the data item? The data item is 6. The weight we're looking for is 6. So that's 6. The mean is 7. The mean weight is 7. The standard deviation is 0.8. We'll put it into a calculator, and we come up with a negative, of course, because 6 minus 7 is a negative 1.25. So what does that tell us? This tells us a weight of 6 pounds is 1.25 standard deviations below. Why below? Because it's negative. The negative tells us we're below the mean. Okay, let's take a look at this on the normal distribution graph. Now, you'll notice our standard deviation is quite small, so our data really is clustered very, very tightly against the mean. I'm going to try to draw that. So let's see here. I got this. So what this means is that really we have a normal distribution. It's still a bell curve, but it's very tight. It's a taller, tighter bell curve because we have such a small standard deviation. Okay, so here's our mean. This is our mean. And we still have a +1, we have a +2, and a +3. And I've kind of randomly put these on here to some degree. Okay, and we know from our data that the mean is 7 pounds. If we add if we add 1 standard deviation above we add 0.8, we get 7.8. Add another 0.8 to get to 8.6 pounds. Add another 0.8 to get to 9.4 pounds. Now let's subtract 0.8 to go below the mean. 6.2, 5.4, and 4.6. So you can see again using our 68, 95, 99.7 rule. 99.7% of newborns are between 4.6 pounds and 9.4 pounds. Okay, they're clustered very tightly. Are there babies that are heavier? Yes. Are there babies that are lighter? I think I call these premature or preemies. Of course there are. But the vast majority of us are normal when we come out as a newborn, and we'll be between 4.6 pounds and 9.4 pounds. How about our 6-pound baby, our 6-pound newborn? Well, you can see right here, if this is 7 and this is 6.2, our 6-pound newborn is approximately there. That's our 6-pound newborn, and it's a little lower than 1 standard deviation below the mean. As we calculated right here, it's actually 1.25 standard deviations below the mean. But I wanted to make this normal distribution a little bit tighter because of how small the standard deviation is. Let's look at one more example, I believe. Then we'll do a little bit of algebra. We'll do a third example with some algebra. Okay, so this example is when I talks about comparing. Okay, comparing scores. Give me a second, straighten myself out. Okay, I think I'm good. A student scores 70 on a math test and 66 on a vocabulary test. Okay, well, obviously, the higher score is 70 on the math test than it is on the vocabulary test, is 66. However, the scores for both tests are normally distributed. The math test has a mean of 60 with quite a large standard deviation, a standard deviation of 20. The data is quite spread out for the math test. The vocabulary test has the same mean of 60. The standard deviation, however, is only 2. These scores were quite compact, quite close together on the vocabulary test. On which test did the student have the better score? Now I'm differentiating better from higher. Here's the higher score, 70. We'll assume like a 70% and a 66%. But which score is considered better, and when better be kind of relative? Which score is, when it comes to looking at the class, which score was better? Okay, so let's remind ourselves. The Z-score is equal to the data item minus the mean divided by, and I'll just abbreviate, the standard deviation. Okay, let's look at the math test. So I'll come over here to the math test. Okay, the math test has a Z-score. The data item is a 70. The mean on the math test is a 60. The standard deviation on the math test is a 20. We'll do this math and we'll come out with a positive 0.5. Okay, now let's look at the vocabulary test. So the vocab test. Okay, let's look at its Z-score. Again, the student had a higher score on the math test, but let's see how the Z-score turns out relative to the test itself. Data item is 66 minus the mean, which happens to be the same, divided by the standard deviation, which is 2. These scores were much closer together, and it turns out that this one is a +3. So on the math test, this student was only 1/2 of the standard deviation above the mean. On this test, the student was 3 standard deviations above the mean, way up there relative to everyone else. So here's the better score. Okay, let's take a look at this graphically. Now, this has quite a large standard deviation. So this curve, I'm going to try to draw it. This curve is quite shorter, and the bell is shorter and fatter. I'll kind of go like that, and pardon, it's not the perfect drawing, but this is the bell curve for this one. Oh, that's not very good at all. Okay, kind of, sort of. Okay, this has a much squattier bell, if you will. Okay, it's not nearly as tall, and it stays rather wide as it goes out there. And we still have the same thing. We have a mean, which is, the mean here is 60. And we have, now of course, if we're going to go up 20, maybe 1 standard deviation is up here, and that's your 80 score. 1 standard deviation is 20 above. This student scored a 70. Well, that's right here. Okay, so here's the score of a 70 right there. 0.5 standard deviations above. So relative to the class, the student was above the mean, but not by too much. Okay, there were still a fair percentage of scores that were above the students. Of course, there were more that were below, but there were still a fair that are above. On the vocab test, the standard deviation is far, far smaller, so we're going to have a much tighter bell curve. Okay, it's still a bell curve. It's just going to be tighter. The area underneath it is still 1 or 100%. It's just tighter. Okay, so here's the mean. Okay, the mean here is still 60. Now, standard deviation is 2. Well, if this is 80, it looks like we would have a standard deviation of 2, like maybe right about here, right? If 80 is this distance, we got to count by 2. So 80 would be over here. So here is +1 standard deviation, which is 62. Okay, where did this student score? Well, this student scored 3 standard deviations above. This student scored at 66. Here is the student's score on the vocabulary test at +3 standard deviations. And you can see very few students did better than this student. The vast majority did worse than this student. So the better score is on the vocabulary test. The higher score, assuming that they're both, percentages, is on the math test. But that's because on the math test, the scores were so spread out, whereas on the vocabulary test, they were quite close together. And this, the 66 looks like it might have been the best score, or maybe the second best score. Whereas over here, this score is probably, just barely better than the middle score, or the mean score. Okay, let's do an example. We'll do a touch of algebra to find a score that corresponds to a z-score. Intelligence quotients, your IQ, is calculated from the standard Stanford-Binet intelligence test, and these are normally distributed. So our intelligence scores are normal, the mean is 100. And this is saying that the standard deviation is 16. Okay, so the average IQ is 100, and we have a standard deviation of 16. What is the IQ that corresponds to a z-score of positive 2.05? What IQ do you have if I tell you your z-score is 2.05 standard deviations above the mean? Well, what do we know? The z-score is equal to the mean, the data item minus the mean, the data item minus the mean, divided by the standard deviation. Well, in this case, we're looking for the data item, so let's put in the other three things we know. We know that the z-score is 2.05, so I'll put that in for z-score. We don't know the data item. We're looking for it, so I'll write it with an X. We know the mean is 100, and we know the standard deviation is 16. So we want to solve this equation for X to come up with the IQ score that gives a z-score of 2.05. So I'm going to multiply both sides times 16, and I come up with 32.8 is equal to X minus 100. I'll now add 100 to both sides, and it turns out that X is equal to 132.8, which of course is the IQ score that has a z-score of 2.05. So the person who is 2.05 standard deviations above the mean has an IQ just a touch below 133. So there you have it, a fair amount of work on z-scores that allow us to get beyond the 1, 2, 3 standard deviations and to work with standard deviations that are different, that have a partial 2.05, for example, or negative 1.5 standard deviations, etc.